You're probably watching this video on your computer or tablet right now. Have you ever wondered what makes it possible for you to see what you see on the computer screen? As some know, the colors we see are due to the way the molecules of materials absorb and reflect electromagnetic waves. So how could a computer screen be so flexible in the way that it shows colors? The answer is liquid crystals. Have you ever heard of an LCD screen? Many televisions and screens use LCD displays or liquid crystal displays, especially those from a few years ago. Game Boys, calculators, and even modern electronic watches still use LCDs. However, recently there have been new developments of screen technology, which are leaving LCDs in the dust. But LCD used to be the major player and is still a fantastic method. So what actually is an LCD? As the name suggests, liquid crystal display, what we see on the computer is all possible due to the use of liquid crystals. The name liquid crystal may sound oxymoronic, because crystals are solids, right? Well, not always. Liquid crystal is a state between a solid and a liquid, and that's only possible at very specific conditions. There's a very small range of temperatures in which liquid crystals can exist. There are many different types of liquid crystals, but the most common one, especially in screens and displays, is called the nematic liquid crystal. In the nematic phase, all the liquid crystal molecules, or mesogens, all point in roughly the same direction. The direction can be called orientation, which means the liquid crystals in the nematic phase have an orientational order. However, they don't have positional order, which means that the mesogens are always flowing and moving, similarly to a liquid. Liquid crystals are exactly in the center of solids and liquids in terms of the way their orders behave. Solids have both orientational order and positional order. This means that the molecules point mostly in the same direction and don't move much. Liquids don't have orientational nor positional order, which means that they flow and move much more wildly, and they don't point in any average direction. Why do all these mesogens and orders matter? How does it relate to screens anyway? Well, they're used in creating the light and colors that come from a screen. The liquid crystals are important because of their unique properties, how they act in an orderly but not absolutely solid manner, meaning their flexibility. Different pixels are separate cells that all work in the same way. There are liquid crystals that are sandwiched between two polarizing films, and polarizers are materials that block out light. So these polarizing films are placed at 90-degree angles to each other, so that when light passes through the first film, it can't get through the second, thus creating a black spot. But then if the top polarizing film is rotated a full 90 degrees, light is able to pass through both of them. This light comes from behind, so as you look at your screen now, white light originates from the very back of it, while the second polarizing film is the last layer, although glass is usually put between the screen itself and the outside world for protection. Well, back to the polarizers. It's actually highly impractical and inefficient to physically rotate the polarizing films themselves, so mesogens in that twisted nematic phase are used. This means that the mesogen closest to one polarizing film is perpendicular to the mesogen closest to the other polarizing film. As light enters the cell, the polarized light follows the direction of the liquid crystals. Therefore, the state or direction of the liquid crystals determines the brightness of the spot. When an electric current or a voltage is applied, the mesogens twist to have the bottom and top mesogens in a parallel position, which then makes light not able to pass through the second film, creating a dark spot. The amount of voltage applied determines how bright or how dark a pixel is. However, in our modern and futuristic day and age, screens aren't just black and white. They have millions of colors, so how come these cells or pixels only determine brightness? Well, that's not entirely true. A part that's smaller than the pixel is responsible for colors called the subpixel. Does the term RGB sound familiar? This is because the subpixels of your screen consist of red, green, and blue. A single pixel in the screen consists of one red, one green, and one blue subpixels. The way the cell works is this. There are electronic transistors and capacitors on glass plates, where color filters are added in alternating RGB colors. On top of these transistors, a thin layer of a material called indium tin oxide is usually deposited, which acts as an electrode for the glass plates. Then these plates are glued together, but with a space in the middle, and that's where the liquid crystals are placed. Finally, the polarizers go on top of those layers, oriented at 90 degrees to each other as stated previously. When voltage is applied to, say, a blue subpixel, the messages go from the twisted nematic phase to the untwisted nematic phase, which causes them to line up with the electric field. This allows polarized light to reach the second polarizer, which then absorbs the light. Since the second polarizer absorbs the light, no light ever reaches the screen, so that subpixel looks black. When there is no voltage, the messages go back to the twisted perpendicular state. The polarized light is then able to pass through the subpixel, and through the second polarizer. So if the green subpixel, for example, has no voltage applied to it, green light will be transmitted in that area. When different subpixels allow light to get through, the colors will mix together, giving the pixel a very specific color. When all of the subpixels allow the same amount of light to pass through, the pixel displays white light. This is because when red, green, and blue are equally mixed together, our eyes see that as the color white. The amount of voltage decides on the orientation of the liquid crystals in a subpixel, which can create different shades of colors. To describe how complicated a computer screen is, I'll check my own laptop screen's resolution. You can do this as well by finding the system information about your display. My screen's resolution, for example, is 1280 by 800, which means that there are 1280 times 800, or 1,024,000 pixels in my screen. This means that there are 3,072,000 subpixels in my laptop screen. The fact that there are so many subpixels and so many different combinations of orientations means that there are millions of colors and billions of possibilities of what my computer screen can display. These are the basics to how relatively simple screens work. Nowadays, more advanced technologies are being used, such as LCOs, plasma, and OLED, which have better quality and more possible color combinations. However, they're less reliant on the liquid crystals and are much more complicated, and so should be left to be studied on another day.